So you recall, I'm sure, from Tuesday's discussions that I talked about these musical instruments and closed pipes and open pipes. Right? So we talked about them. So why are we doing this? Because I want you to know that once you have the geometry of a pipe, basically a pipe, of course, is you can regard it as a cylindrical, long cylindrical object. You can also regard it as a long box. It probably won't make a great deal of difference. But the important thing that you are after is figuring out how it's designed at the ends. Okay? So we discussed this. If you go back and look at the lecture notes, you will see that. So you can have a situation where both ends may be closed. All right. Now that won't be a very useful musical instrument, as I said, but theoretically it's a fantastic pipe where all the things that's happening here can also happen here, but in a slightly different way. So the idea is that you get to figure out how to do these drawings, because once you do the drawing, the rest of it falls in place. The first thing that you would notice is that there is some kind of a length given for this pipe. That length is very important. So if the pipe is small or the pipe is large, meaning length is small or length is large, that has a role to play in what kind of frequencies will come out of it. So for example, if it's very long, the frequencies that you will get out of it will be different from when it's very short. So that's one important thing. But before we can get to what frequencies are allowed or disallowed, what we must recognize is whenever you have a closed end, there can't be any vibration in a closed end. So therefore, you will have what we were calling nodes at the closed ends. So clearly, in a pipe that's closed at two ends, you have two nodes. Whereas a pipe that's closed at one end, you have only one node. And that has a big role to play in what kind of amplitudes will be permitted as far as vibrations are concerned. So now we are drawing the amplitudes. So let's say there is no vibration here, there is no amplitude, but here it's completely open. And because it's completely open, logically you would expect that most of the vibrations will be in the open end. So basically what will happen is that if you were to plot the amplitudes, the standing wave will look like this. In other words, if there is sound propagating through this pipe, this is the kind of vibration that will end up with maximum amplitude vibrations happening here and minimum vibrations happening on the other side. Okay? Now, in this case, on the other hand, this particular configuration of amplitudes won't work because clearly you have nodes at both ends, and the only way you can get nodes at both ends, the lowest vibration mode would therefore be kind of like this, right? Because at both ends you can't have any vibrations. There's no vibrations at the ends, and therefore this will be the way the amplitudes will shape up, with the largest vibrations, largest amplitude vibrations showing up in the middle. So now what you do is you relate this to the wavelength of a wave. So for example, you know very well that if I start from minimum to maximum like that, so that's a full wavelength, that's covering a full period, right? So this is my lambda. So you draw that quickly. This is your lambda. And if this is your lambda, then you can easily see that over here you are really going from here to here. Now you can say, what? Guys, can you sit down? Why are you taking so long to sit down? Just sit down. So now you can see that what I have drawn here is also a standing wave. So let me now come to that. And this is also a standing wave. So there are all these delicate components to the understanding that I wasn't really sure if you guys got it. So that's the reason why I thought I'd quickly go over it. So in other words, here, if you, for example, have a wave going from here to here and then reflecting off this end, and the standing wave would be, as this reflects off, it'll be like that. So you see it begins to look like that now. So in other words, you have back and forth, the wave is going back and forth like that in standing wave. Just like, remember I was telling you that if you have vibration of a string, this thing is being shaken, you actually have some kind of a standing wave pattern that will develop. You can do that with a string and an end. Just vibrate it and you'll see that it goes both ways, and if you look at it, it kind of looks like, it's an envelope. So in other words, here, for example, you're really going from this point to that point, that's 1/4 of lambda. So therefore you have this wavelength that is the wavelength that is being captured, therefore, is 1/4 of whatever lambda is allowed. And so L hence must be equal to lambda over 4. This is something we did on Tuesday. L must hence be lambda over 4. Here, on the other hand, this is going to be lambda over 2, because that's like going from here to here, right? So lambda over 2 is therefore going to be L. So once you fix L, you automatically figure out what lambda is going to be allowed. And this is why I was saying that depending upon the value of L, the lowest lambda, this is the lowest lambda that is allowed, is something that you find. Question. Do you guys get it or no? Because I'm going to be asking you quite a few questions on this. Yes?
So how is it lambda over 4?
Oh. Just think about the standing wave. So this piece is basically this piece, right? So this is 1/4. Right? And that's the lowest frequency. Now, the next higher frequency, for example, can be, again, you have to have an opening here, but you can certainly have this. No, actually, the next higher frequency would be this. See? So this is your L, and this is going to be lambda over 4, another lambda over 4, another lambda over 4. So here you'll have L equal to 3 lambda over 4. Because 3 lambda over 4 will give you a higher frequency than that. You guys get it or no? So if I give you a length, can you calculate the wavelength? Yes or no? Shake your head or don't shake your head. Right way or the wrong way? Come on. This is not good. All right. So if I give you L, now you know lambda. You know the sound velocity in air. It's about 300 to 330 meters per second in normal temperatures. So V, we already know the velocity is distance over time. So that's the wavelength lambda traveled over a period of time t. We discussed this already, right? V is lambda over t. So therefore, 1 over t is frequency. This is lambda times frequency. So once you fix L, right? So L gives you lambda, and lambda then gives you, because V is fixed, frequency. So that gives you the frequency. Whether you are getting a low frequency, or you're getting a high frequency, figure it out. That depends on all these things that's happening. All right? Okay. I don't want to entertain you anymore. Now let's get down to some other things. I don't think Doppler is that difficult, so you should have no trouble with Doppler. But let's get back to the issue of the hydraulic jacks that we were discussing. So in the fluids piece, we had drawn this thing, right? And you remember that in a static fluid, the pressure must be the same everywhere. That was one of the important things that we touched upon on Tuesday. So I have a fluid that's here, and I have a fluid that's here. So this is my fluid, okay? And then that pipe connects the fluids on both sides. And as we discussed, the pressure must be the same everywhere, especially in this case because the fluid is at rest. If the fluid is not at rest, then a lot of complicated things can happen, and we will discuss this today briefly in a little bit. But right now, let's first clearly understand that if the fluid is at rest, pressure is the same everywhere. So now suppose, let's use a different colored chalk. Now suppose I put in a piston on both sides. So I put in a piston here. Piston is something like this, and I put in a piston here. Let's say something like that. So I now apply a certain force here. Let's call it F1, and let's call the cross-sectional area here A1. So A1 is therefore pi times whatever it, if it's circular, for example, it's R1 square, where R1 is this radius. And likewise, if this is circular, I can call this R2, right? So therefore, the area here will be A2, and A2 will be pi times R2 squared. All right. So the idea is that the pressure that you're going to get, this pressure P, is force per unit area by definition, right? So therefore, if I divide F1, which is the force, by the area A1, that should already give me the pressure that I am putting into the system. And what the fluid does is, a static fluid would instantaneously transmit this pressure everywhere. So therefore, every point in the fluid now knows what the pressure must be, and therefore the same pressure must show up at the other side, which means since you know A2, you fix A2, you design the system, that also then fixes what F2 must be. Because if A2 is large, then necessarily F2 should also be large. So this is a very interesting problem, because you can actually generate very, very large forces by simply manipulating and arranging the system just the right way. All right. So now one of the things that I want to bring up is the issue of work done. Normally, the advantage of a press like this is that you can make this relatively small, you can make this relatively large, you can apply a modest force here, and that will generate a very large force there. But you can't get something for nothing. Nature doesn't like that. So what happens is that, yes, you have a very large force on the other side, but that very large force can only make very small movements. So in other words, suppose I put my foot here. This is my foot here. I can put it on that. And I actually put a very heavy object here, maybe like a car. This is not a very good drawing. So then, of course, my foot is extremely, it can exert an extremely small force compared to a car. But let us say that I can do, the amount of work I can do is I can apply a small displacement d1 here. So F1 times d1, then this must therefore, this is the work done, right? This is the work done by my foot. And since energy must be conserved, F1 times d1 must be equal to F2 times d2. So this is also the same work done, W. So if F1 is what I apply, and d1 is something that I put in because of how hard I press this piston, I already by design am getting a very large F2, right, in this case, which means that d2 must be small. So if this is large, right, if this is large, this must be proportionately small. That's the whole idea. So in other words, if I want to raise something like a car up on the right side here, I have to keep on pumping for a while, such that every time I pump it, I give a significant amount of D1 and a significant amount of F1, and then I get a big force F2 with a tiny little D2. So if I pump it maybe 30 times, it can be enough work done to lift the car up to a point. So that's the whole idea. That's how hydraulic jets work. Any questions on the hydraulic jet? Okay. So, assuming that you guys get it, so as you can see, the problems with these parts are not difficult, they're easy, but it's important that you understand the conceptual foundations of it, because if you don't, then you can't do it. You either can do them or you can't do them. It all depends upon whether you get the conceptual foundations. So let's now get into the idea of fluid pressures a little bit. Okay, so let us say we look at air. It can be any fluid, but let's say we look at air for now. And just to be clear, we take air, let's say a slab of air. Imagine that you have, this is not a real material, just you imagine you have taken a slab of air. You have defined some boundary within which you're going to consider air. And let us say this slab that you have designed has some thickness, delta y. Delta y. So you can see that there are all kinds of forces that will be acting on the slab. Let's say there's an area associated with the slab that I can design. I can define A. And let's say there is a density associated with the fluid here, which I can describe by the standard symbol for density, rho. Furthermore, because it is air, and since I know that air is a gas, gases typically tend to be denser at lower levels and less dense at upper heights. So this rho will generally be proportional to the height y. So I would just mention its dependence by writing rho y. Okay? So now I already know that this is just normal slab of air, which means there will be some kind of pressure from above, force from above, because the entire atmosphere is pressing onto it. So there is a force F2 from above. So the idea here is that all of us are actually living at the bottom of an ocean, and it's the ocean of air, right? So on the surface of the earth, the entire column of air from here on to the edge of space is actually applying pressure on us. Now we are designed to withstand that, so you don't feel it. But if you go to a high altitude, then your body responds differently, because the air pressure goes down quite a bit, and you can get tired more easily, and so on and so forth. So all these things happen because of air pressure. So our bodies actually are quite tuned to the air pressures in which we live. So for example, in Buffalo, we are a few hundred feet above the sea level, whereas if you go to some place like Denver, for example, it's about a mile high, or Albuquerque, it's about a mile high. So a mile high, the pressure is quite a bit lower for our body. We would adjust in a few days, but if we just get off from the plane and go for a run, assuming you fly in, you'll probably get tired very easily. You may not, in fact, be able to do your normal run, or even a brisk walk. You'll get more tired, and that's because the air pressure changes. So we are always under some kind of force or pressure from above, and that's that. But pressure is something very strange. When we think about pressure naively, we think about pressure from the top. But pressure can be from the side. Pressure can be from below. Pressure can be from every direction, because pressure is a scalar. It's not a vector. So in fact, therefore, this slab is subjected to two forces, one from above and some other force from below F1. It may or may not be same as F2, so I'll just keep it F1. So the mass of this slab, delta M, is going to be the density times the volume, and the volume would be the cross-sectional area A times delta Y. Right? Mass times volume, that's what, density times volume, that's what mass is. So if I now write down the forces that are at play on this slab of air, then the forces are going to be F2, F2 is downward, minus F1. Now this slab is in equilibrium, so right hand side must be 0. And I also have mg acting downward. So actually I should take F1 to be plus because F1 is upward. So let me just rewrite it as F1 minus F2 minus delta M, which is the mass which I just computed, times G is equal to 0 because it's in equilibrium. These are all the forces involved. As you can see, F1 goes upward. So F1 is therefore on the F1 therefore at the plus sign, just the way you have done before in constructing force equations. F1 minus F2 minus delta M equals 0. So we can actually simplify this equation because F1 can be thought of as P1 times A. P1 is pressure here, minus this would be P2 times A minus A times delta Y, that's the volume, times the density rho Y times G. Okay? Any problem? Yes? Density times volume, so that's mass, right? This is mass, right? This whole thing is mass. Any other questions? Okay. So now you see I have A everywhere. So this is pressure. I've just converted this F2 to P2 times A and this F1 to P1 times A. Here. So therefore I can cancel out the A's and I'm left with P1 minus P2 minus rho Y delta Y times G equal to 0. Therefore I can write since P2 should be larger, presumably I can write P2 minus P1. Okay, so that's P2 minus P1 divided by delta Y. This is just a way of writing the same thing. I'm not doing anything different. Is minus rho Y times G. So in other words, I've just rearranged it. I've taken P2 to the other side, so P2 becomes positive, P1 to the other side, P1 becomes negative. So flip that, divided both sides by delta Y, so delta Y goes away, and I'm left on the right side with minus rho sub Y. Product. This turns out to be a very important equation for us. And it's an equation that describes hydrostatic pressure as a function of height. Hydrostatic because the fluid is not moving. But it has an interesting thing to say already. It basically says that because the right side is negative, P2 must be less than P1. So in other words, as you go upward, your pressure will go down. That's what it says. That's what this negative sign here implies. The negative sign means that as you go up, pressure goes down. That's exactly what I said when I was talking about going to Albuquerque or Denver. So as you go up, the pressure, air pressure, goes down. One would write this in the form of what is called Pascal's law. The other thing that we did over there was Pascal's principle. So just so that you know. So P2 minus P1 therefore is often written as minus rho G Y2 minus Y1. So in other words, if you want to draw a picture, it basically means that this is the pressure at an upper height, P1, and then you have Y2 at this level and Y1 at this level. And just if you notice, I have actually made rho Y equal to rho, which means I've ignored the fact that as I go from Y1 to Y2, my density changes. I'm ignoring that. I'm assuming that the density change as I go from Y1 to Y2 is very little. So this therefore is my air slab. That's what I've tried to draw. Okay, and the density is, I've assumed, doesn't change very much. So I've said they're about the same. This is the lower height, this is the upper height, and therefore this is the equation that now comes around, and this equation is often referred to as Pascal's principle. So if I tell you to work with Pascal's principle, that's what I'm asking you to do, and that is something that I probably will do, because it is a very critical part of what we are learning in terms of how pressure falls. By the way, when the weather part of the news talks about air pressure and so on, a lot of that discussion centers around something as simple in the first instance as Pascal's principle. So this stuff is something that you actually hear pretty much every day if you're listening to the news. So how does this work then? Basically all it says is that P2 minus P1, so pressure at a higher level minus pressure at a lower level, has a negative sign, so pressure falls. It depends upon the density of the material. So in this case we were talking air, but it can be any fluid. Acceleration due to gravity G. So in other words, you can imagine that in Jupiter, as you enter Jupiter, first of all, density of the gases involved are different than on Earth, but the acceleration due to gravity, because Jupiter is so large, is incredibly large compared to what we are used to. And therefore, even going a small depth in Jupiter will result in a large pressure change as you are entering into the Jupiter atmosphere. So, but you know, a simple equation like this already gives you those details. You can calculate the G for Jupiter because you can, for example, figure out what the mass of Jupiter is using various techniques, and you know, you can get a sense of how pressure will change in Jupiter if you know roughly what the density of all the gases there might be. All right. So now let me just give you a piece of wisdom. So let's say, as I said, we are at the bottom of an ocean. So let's say here you are, and this is ground level. So let's say I put, hypothetically, I would never do such a thing, I won't be able to do such a thing, but suppose I can put you in a cylinder, in a glass cylinder, long one. So this is my glass cylinder, there you are. This is the ground level, as I said. And suppose the cylinder is long enough such that it goes to the edge of space. So this is roughly where the atmosphere ends. Now, edge of space, of course, it's an interesting thing to say, but it's not quite an edge, because basically what happens is as you go higher and higher and higher, the density goes lower and lower and lower until it pretty much thins out to an extremely small number, such that the actual air molecules that you see at that height would be literally minimal. And that's pretty much where you reach space, and the pressure drops to effectively to zero, and so on and so forth. So by edge of space, I'm kind of making that kind of remark. So this really literally is your ocean of air on top of you. So question can be, what is the pressure that you are enduring? And it turns out, if you actually measure it, this pressure will come out to roughly 1 kilogram per. Actually, the density of air at sea level. This is the rho at sea level. 1 kilogram per centimeter cube. Centimeter square, because it's an area. And it turns out that the corresponding pressure here is roughly 10 to the 5 newtons per meter squared. So each of us at any given point in time are carrying 100,000 newtons on us. We don't feel it because we are designed not to feel it. Our bodies are designed in such a way that we don't feel this 100,000 newtons roughly that's sitting on us. So it's not just pressure from above, by the way. This is very important to understand. So if I stick my hand out, you can argue that the amount of pressure from above is going to be 100,000 newtons per meter squared. My hand is very small, so it's not really even close to a meter squared. But if it were a meter squared, which is roughly 3 feet by 3 feet, then it would be 100,000. Now it turns out that if 100,000 newtons were tested on my hand, it will probably go down, but it doesn't. In fact, I have no trouble putting my hand out like this, which also is indicative of the fact that that's balanced, which means there is 100,000 newtons from here also. Which means there's 100,000 newtons from here also, and from every other direction, because pressure is a scalar, as I said. It is not a vector, and pressure is everywhere. This is a very important thing to understand. So when we talk about pressure, it's not just pressure from above, but we live in an environment where pressure is acting on us from all directions. So how do you even get to the point of measuring what I just discussed? How do you know that I'm not lying to you? How would you ask a question to figure out what I'm telling you is reasonably accurate? Well, you can do a relatively simple experiment in which you can take, let's say, a bucket full of water. So you take a bucket full of water, and you take a clear pipe, and you just put it in the water. It's not a snake, it's a pipe. So if you do that, then you'll find that the water level will rise a little bit. You have kept the top of it open, so water level will not rise very much. It just rise a tad bit. So one can argue that the pressure on the water, on this side, on every side, is actually the pressure from that atmosphere. And this atmospheric pressure, because this is open, it's also acting here, and therefore the height of the water is about the same. It doesn't really change. However, if any of you, I'm sure you have, played with straws when you are drinking some pop or something, you know very well that if you actually take this pipe and actually put your finger here, then what will happen? Will the level of fluid rise or fall? straw, you haven't been drinking much lately. It's going to rise. You need to drink a little more. Because you've never taken a straw when you're drinking pop or something. You guys are so terribly worried. I've never encountered such worried kids. You take a straw, stick it in a glass of water, put your finger on top of the straw, and just observe. You'll actually find that the liquid level creeps up in the straw. Do the experiment today. Don't you have a straw there? No. You have a straw over there. Do the experiment. Huh? That doesn't matter. You'll find the liquid level right. And she has a plastic straw. Sophia has a plastic straw right there. Yeah, put your finger on top. Yeah, you can't see a damn thing because it's opaque. But you will find. Alright. So anyway, the liquid level rises up. And that actually is very interesting in this case because the liquid level has a role to play with air pressure. So let's try to understand this a little bit. So actually your pop with a transparent straw becomes a barometer. That's what it effectively becomes. So essentially you can take the bucket. And here you have your fluid, static fluid. And here let's say you have a closed cylindrical pipe. So you will find that the liquid level, depending on what liquid you have, will rise to a certain point. So over here the pressure is P atmosphere, right? So no big deal there. But it turns out that over here, the things change a little bit because this point is closed. If this point is closed, the pressure here is the atmosphere, but actually the liquid can rise up to reduce the pressure it feels. Because as it rises up, the pressure goes down. We already know that from what we just calculated. So in other words, the maximum height it will rise is controlled by the fact that what height it can get to, this height here, to make the pressure here roughly equal to zero. That's what it does. That's the reason why the level of the liquid will rise. Everybody is using opaque straws here. That is P roughly equal to zero. Okay, so this is almost, you can assume it is. Not all fast food places give you transparent straws. Yes?
So why is it when you so if you have your finger on the straw and you kick it out, why does the water stay in the tube after you
It actually doesn't, it will go down. When you put the finger on the top, you are essentially allowing the fluid to rise such that it gets to roughly zero pressure, very low pressure. But if you now release your finger and let the straw become open, you will see that the level will fall. That's what it is. Unfortunately, none of you have transparent. There was a time when only Burger King used to do transparent straws. So I used to go to Burger King to pick up transparent, not to do this experiment, but for other reasons. And not read Burger King burgers necessarily, but I was doing some experiments with some nanomaterials and straws, and I would have to go to Burger King often to pick up the straws. But anyway, you can do opaque straws are good. You don't believe me? You guys should do this experiment after class today, and then report back. Maybe that should be your homework. All right. So now you see that we actually can go back to our Pascal's principal business here, and we can write P2 minus P1. In this case, P2 minus P1. Just write P1 minus 5, right? P1 minus P2. And the minus sign goes away. On the right side, I have rho, the density of the fluid, I have its original gravity, and I have the height h that I do over here. Now, if I assume, so P1 is here, and P2 is this one here. if I assume that, so let's assume that P2 is roughly equal to 0, then I can write P1 is approximately equal to rho G. So do you know what usual barometers are made of? What liquid it contains? You guys don't know? Come on. So when they talk about barometric pressure during news, what is the liquid that? It's a pressure of what liquid? They talk about 76. Yes, 76 centimeters of mercury, or 760 millimeters of mercury. So if you look into the detail of how the pressure is reported during news, you will actually say that the pressure is 76 centimeters of mercury. Now that shouldn't make sense because the unit of pressure is not centimeters. But what they're talking about is that the density is that of mercury. Mercury is denoted by Ag. G is fixed. And the height attained by the mercury column is 76 centimeters. That's what they're talking about. So they're actually reporting to you a number that is based upon Haskell's principle. The density of mercury, by the way, this density, mercury density, or the G, is 13.6 times 10 to the 3. Mercury is a very, very dense fluid, kilograms per meter cube. So if you do all the numbers, then you will see that you get roughly the numbers work out to 1.03 times 10 to the 5 pascals. Pascals is newtons per meter square. Is approximately equal to 13.6 times 10 to the 3 kilogram per meter cube times G, right, 9.8 meters per second square times 0.76. These are the numbers. 0.76 meters is of course 76 centimeters of mercury. So those are the, if you multiply out, you'll see that the numbers on both sides roughly match up. So in other words, to get to atmospheric pressure, this is the atmospheric pressure. Remember I told you it's 100,000 liters per meter square, so that's where this number comes from. The atmospheric pressure is this, and so this is equal to the density of mercury, so this is rho Ag here, times G times H, and H is 0.76 meters, 76. So there is no reason why all the barometers have to be made of mercury. You can always make a barometer out of water. Water is a perfectly easily available fluid, and so instead of taking mercury, I can make water. But the trouble with water is that the water's density is much lower. It's only about 1,000 kilograms per meter cube. It's a factor of 13.6 times lower. So because the density is lower, to match up with the left side of the equation, H must be higher. And for that reason, we don't use a water barometer because it will have to be a huge engine getting up to tens of meters to be able to get up to pressure. So who would want to do that? You need something to look up there. So it's better to use a denser fluid, and mercury is a very stable denser fluid that one can use for our purpose. And this is the reason why one uses a mercury barometer. Let me now move to something important, and this is Archimedes. Archimedes' principle, of course, goes back to Archimedes. Long time ago, I forget the years now. I'm embarrassed to know this. But the idea of an Archimedes principle actually is rather beautiful. Suppose I take an object. For convenience, let's take a cylinder. And I put the cylinder in a fluid. And I make sure that the cylinder is not, super heavy so that it doesn't stick in the fluid. arrange for it to be just about the right material, the mass, and so on, such that it flows in the fluid where I put it. And let's, for argument's sake, say that it flows by being partially submerged, not fully submerged. Of course, once we work it out, we can fully submerge it, and there is not going to be no problem. So let us say the cross-section area here is A, okay, and let's say the length of this is L, okay, and let's say the height by which the lowest part of the cylinder comes up to the level of the liquid is H. So we need all these parameters. So the cross-section area is A, and the pressure here can be P2. Cross-section area here can be the pressure here can be P1. So one can think about an F2 here, like before. One can think about an F1 here, and this can be the density of the fluid rho Q. And I can also assume for now that the density of air compared to density of fluid is roughly equal to 0. In other words, it's almost like that. It is not, but as far as I'm concerned, because it is so much smaller than the density of the fluid, I can just assume that the density of the fluid is all that matters, the density of air. This is air. So the idea again here is from Pascal's principle we can say F1, which is the one below, minus F2, which is the one from above, minus area times density of the fluid times G times H. This is what Archimedes basically said happened. Archimedes basically said that F1 minus F2 actually balances the displaced mass of the fluid. So you see this is partially submerged, as I said. So this part of the volume of the entire cylinder is underwater. So if you look at what I've done, is the density of the fluid times the cross-sectional area times the height. So this is actually, if I write down here, let me just rewrite it by writing the height here and then G. Then this is the piece which describes the mass of the displaced fluid because the cylinder is submerged. But this is the idea of Archimedes' principle. In other words, when a ship is floating on water, is a displaced fluid by the ship. It means the amount of the ship that's underwater, that is tied to the displaced fluid. Okay? So that is the weight that counts. Therefore, F1 minus F2 is actually equal to this point here. But this is the basic idea of Archimedes' principle. Yes?
Where's F1 at? Like F2 represents like
F1 is the force from below. Again, there's a pressure from every direction, right? So there's a force from below, force from above. There's a liquid. There is no reason to assume that the liquid is not going to give you a resistant force. So if you are by Newton's third law, you will have some kind of reaction force resting from below. They can look at it like this, but the other way of thinking about it is that there's pressure everywhere. So instead of writing just the force, you can write the pressure. And then it's more, it's a little bit easier to see why. So if I now think about this F1 as P1 times A and F2 as P2 times A, then I should be able to rewrite Archimedes' principle in terms of Pascal's law as P1 minus P2 is rho fluid times P, in this case times H. Now, the idea of Archimedes' principle is to introduce the concept of a buoyant force. So what is a buoyant force? A buoyant force actually is F1 minus F2. So this is the buoyant force. So what does the buoyant force tell us? Buoyant force basically tells us that the total weight of this whole cylinder, including the stuff that's above the fluid level, that total weight of the whole cylinder is actually balanced by the weight of the displaced fluid. That's what it tells us. And this equation basically describes the forces and the amount of displaced fluid via Pascal's principle. Think about it a little bit. It's not really all that trivial. The idea is that the reason why when you get into water, you can't stand on water. Why? Because our densities are very close to that water. So therefore, if we go in water, we don't naturally float unless we arrange our bodies in the right way, right? So our density is about 70% of that of water. And this is the reason why you can always, lie flat on water and float, because you're just a tad bit lighter than water. And in fact, you'll find the water level is pretty much up to your nose. It's that you're almost submerged, but not yet. So, in other words, our entire body weight is what's downward. The amount of fluid we displace when we get into water is what is giving you this quote-unquote buoyant force. That buoyant force effectively acts upward, and that's why these two forces will balance. My weight versus the amount of water I displace will balance, and that will be upward, and hence I will drown. Now, if you go to the Dead Sea area, you know very well that Dead Sea has very high density, because Dead Sea is very salty. As a result, the density of Dead Sea water is much higher than normal density of any kind of saline water that you see in normal seas. And because there is so much salt in this drying sea, the density is more, which means it is very easy to float on the Dead Sea. You can't almost drown. I've never been to the Dead Sea, so I haven't tried this, but I'm told by friends who have been there that it's almost impossible to drown because the density of water is so high. So in other words, when you try to float, unlike what would happen in a swimming pool or on the ocean, if the ocean is still, you will float at a level where you're almost submerged. Whereas in the Dead Sea, that's not at all the case. You're floating in a way that a larger part of your body is going to be, outside the water level. So the concept of the buoyant force, therefore, was what came from Archimedes' work. So just to summarize then, an object like this is displacing a certain amount of water. The idea is that this displaced water, the weight of the displaced water, which is here, is what gives you the buoyant force. So this buoyant force is actually effectively acts upward. So in other words, if I were to draw a cartoon of this, the effective picture is, this is my cylinder, this is the water level. This cylinder has a mass m and a weight g, so I have mg for the entire cylinder, and then I have a buoyant force, F buoyant, acting upward, and F buoyant is given there. So this is the picture you should have in mind. For example, if you are told that you put a bucket in the waters, and you figure out to what level the bucket has submerged, then you know exactly what is the weight of the bucket, which means you can figure out what is the buoyant force you need to make that bucket float. You know the density of water, and then you can easily calculate what the height h should be as long as you are using Pascal's principle. So this is a multi-stage thinking process. Don't take it too lightly, but make sure you get it such that you have a clear understanding of what you're talking about. So far, I've been talking about static fluids, right? I'm also, by the way, in this case also it is understood that the fluid is greater than the density let me just do it. There is something in fluids called Bernoulli's equation. So that pertains to flowing fluids. So far we have been talking about static fluids, but you can also consider flowing fluids. So let's look at flowing fluids a little bit. And you can imagine fluid flowing through a pipe. And let's say the pipe is not completely uniform, such that on this side, the cross-sectional area of the pipe is A1, and on this side, the cross-sectional area of the pipe is A2. So let us say that the fluid is moving, and therefore there is a velocity. Here the velocity is V1, and here the velocity is some other number, V2. And since, when we talk about height differences and fluids, the pressure is important. Let's talk about the pressure here in P1 and the pressure here. So let us first keep things very simple. Let us say instead of flowing fluid, first, let's assume actually the fluid is not moving. So in other words, let P1 essentially go to 0. So basically it's a static fluid limit. If I turn off the flow, it's like a static fluid. And for this static fluid, from Pascal's principle, I already know that P1 minus P2 is rho g times y2 minus y1. I already know that. That's what we've been doing all day today, trying to understand Pascal's principle, which, by the way, as I said, is only applicable for static fluids. So now I turn on the velocity, but before I turn on the velocity, let me just observe a few things. Here I actually have mass over volume. That's what gives me density. But let's forget about volume for a moment. So I have mg, and then a height difference. In other words, like an mgh. And we know very well by now that mgh is potential energy. Right? You know that. So in other words, the relevant unit here on the right side of the equation is actually energy divided by volume. That's the unit here. Energy divided by volume. So if the unit here is energy divided by volume, then pressure also must be, in terms of unit, energy divided by volume. You can actually check it out, and you will find that pressure has the exact same units as energy divided by volume. So in other words, what I'm trying to tell you is that this equation here is Pascal's law, or Pascal's principle, whatever it is called. Right? Pascal's, I always get confused about this. This is Pascal's law. Pascal's principle is the fact that all pressure is the same. It's making Pascal's law. So this basically is an energy conservation statement. So in other words, if I now let the V1 move, so V1 is not equal to 0, it turns out that all you have to do is to convert the Pascal's law into an energy conservation statement. In other words, you end up writing that kinetic energy rho V1 squared plus V1 plus mg y1 is equal to 1/2 rho v2 squared plus v2 plus mg y2. So this, by the way, this equation But this energy conservation equation, written in terms of mass density, is called Bernoulli's equation. And it is able to describe fluid flow. So I'll come back and we'll do a little bit of this on Tuesday. But Bernoulli's equation is a very important equation for us because it tells us that the pressure in a fluid is actually tied to how fast the fluid is moving. Alright? So for example, let us say in our own bodies, if you go for a run, then the blood flows faster, right? So your heart is beating faster, your blood flows faster. So as you go for a run, what you'll find is that your blood flowing faster will raise the kinetic energy. It will raise the 1/2 rho v squared v squared. And because within our body, this term is not very important because height difference doesn't affect the numbers very much. As this term goes up, as velocity goes up, pressure goes down. And here as velocity goes down, pressure goes up. So this is the reason why, in a simple way from Bernoulli's equation, you can understand that why exercise lowers blood pressure. Because blood pressure is equivalent to the speed. Yes?
So if it's mc/1 squared, it's like the potential. Is it like at a different height or like?
Oh, it's not mg, sorry. It's rho g. Rho g.
Okay, wait, but so what is it like height? Is it like heights or like is it the distance like along the height?
So what I'm saying is that inside the body, y1 and y2 is roughly the same. As far as fluid density is concerned, y1 and y2 contribution will be very tiny because fluid density changes very slightly, imperceptibly. So as far as the body example is concerned, you can drop these two terms, which means you are left with the kinetic energy density term, density meaning kinetic energy measured volume, and pressure term. If you raise one, your pressure. Okay, let's go to the